Okay, so uh, let's start today's class. So, uh, before starting the class, actually, I have tried that last problem that you have told me, like some that assignment 10 question 5. So
Yes, yes.
yeah, so I have tried this problem. So by doing, but this is a very complex way actually have to do it. Okay. I mean, if the answer that is given in the problem, if that is true, in that case, like, you have to use a very complex way. Okay, so anyway, I will show you how to do that. So, uh, 1 second. Uh,
So was that CP by CV formula wrong, which I told you?
so alpha is by alpha p is not CP by CB or something like that. Okay,
Oh,
okay, because that way the answer is not coming right. So the given answer is not matching. Okay. I'll show you. It mathematically looks correct the way I have tried to do. Okay, so the question was like that. Uh, the volume expansivity is given as alpha equal to 1 by v del v del t, right? Then find the ratio of adiabatic to isobaric volume expansivity. That is alpha is by alpha p, and given is Cp is given as 50 joule 50 joule per mole per Kelvin, and Cv is given 42 joule per mole per Kelvin. Okay, so to start this problem, first write what is the expression of alpha. So alpha is basically 1 by v del v by del p, sorry, del v by del t. So 1 by v del v by del t at constant s, and alpha t is 1 by v del v by del t at constant q. Okay. Now, in order to do that, so first what you have to take, v is a function of other two independent thermodynamic quantities, this is temperature and pressure, right? Now you can write, if you take v as this, you can write dv total derivative as del v by del t at constant t plus del v del t del e at constant t, right? Now, if you take the derivative of volume with respect to temperature, uh, 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 by taking entropy as constant, in that case, this relation will become del V del T constant S would be equal to del V del T at constant E plus del V del P at constant P into del P del T at constant S. Okay. So this is the relation we had right now. Now we have to manipulate first this del P by del T thing. Okay. So what we will do now? So basically, you have to play with this term only. Okay. So what you have to do? So we know this relation. So del P del T per into del S del T into del P del S at constant S at constant E and on constant T is equal to -1, right? Now from here you can write del P del T as, if you take these two terms into the right hand side, it will become, sorry, it will be del t del s at constant p into del s del p at constant t. Now it's fine. So del p del t will become minus del s del t at constant p into del p del s at constant t. Okay. Now this thing you can write it like this. You can put this del p del s in the denominator. Then it will become del s del t at constant p by del s del p at constant t. Okay. Now from here, uh, what you can do, you know, Cp is T into del S del T at constant T, right? So that means del S del T will be Cp by T. And from Maxwell relation for thermodynamic potentials, you know, this is the formula, thermodynamic coordinate, sorry, del S del P at constant T will be equal to minus del P del T at constant P. So you write this thing, you substitute this thing here, and you substitute this thing here. Okay. So after doing that, you will get. So this is the expression for del p del t. Okay. So uh, del p del t will become Cp. There is a minus term. So minus minus will become plus. So Cp by T into del v del t at constant T. So, so let's name this equation equation 1 and this as equation 2. So now if you substitute equation 2 in equation 1, after doing that you will get del v del t at constant s will be equal to del v del t at constant t plus del v del p at constant t into sorry, yeah, del p at constant t. This is del v del p. This is del v del p. Sorry. So it will now become del v del p at constant t into Cp in by t into del v del t at constant p. Okay. Now from here you have to use another relations. Okay. So right now this is the state right now we are in. Now from here, basically you have to write these whole terms in terms of Cp by Cp and Cv. Okay. So to do that, what you can do, you know this relation, Cp minus Cv is equal to T into V alpha square by kg. Now here you know alpha is 1 by V del V del T at constant P and Kt is minus del V del P at constant into 1 by V. Now if you substitute both these things here, you will get Cp minus Cv will be equal to minus T into del V del T whole square at constant P divided by del V by del P at constant T. Now from here you can write del V by del P as minus T by Cp minus Cv into del V by del T whole square at constant P of del. So you get an expression of del V by del P that you can substitute here into that final, into our final, like into our main equation, that is the equation 3. Okay. So if you substitute this, let's suppose equation 4. So substitute equation 4 in equation 3. Uh, we get this kind of a relation. Okay, del V by del T at constant S would be del P by del T at constant P minus. So after substituting this here, you will get there will be minus sign will be there. T will cancel, so it will become Cp by Cp minus Cv into del V del T at constant P. Okay, since del V del T square is there and there is also del V del T, so these two term, one term will be cancelled, so there will be only del V and del V by del T at constant P is there. Now what you can do, del V, so this del V del T, so del V del T at constant is, now from here you can take del V del T at constant P as a common, so it will become 1 minus Cp by Cp minus Cv. Okay. Now what you can do, so del V by del T at constant is by del V by del T at constant P. If you multiply 1 by V up and down, so now this right hand side will now become uh, minus Cp into Cp minus Cv, right? Sorry, minus Cv. Yeah, minus Cv by Cp minus Cv. Okay. So 1 by V del T, this is nothing but alpha S, and 1 by V del T at constant P, this is nothing but alpha P. So alpha S by alpha P will be equal to minus Cv. Cv we know is 42. Cp we know 50 minus 42. So it will become minus 42 by 8, that is 5.2. Okay. So, yeah. This is a very complex one. Okay, it's like, so you have to start from this consideration, volume as a function of temperature and pressure. From there itself you get this relation. Okay. Now from this relation, what you have to do, you have to write this del V by del P at constant T. Yeah, del V by del P constant T and del P by del T at constant T. This term in terms of Cp and Cv. So by doing all this algebra and all, so you will get this equation, okay, this final equation, and from there you can write this alpha is by alpha p by this basically. This is the general form. Alpha is by alpha p would be minus Cp into this.
Okay, got it.
Yeah. So I don't know if they will provide any solution or not. Okay, for this problem, but maybe they use some different or easy method maybe to get this kind of formula, like get this particular relation. Okay, that we have to check. Anyway, for right now, this is the way I can figure out. So now we'll move to today's topic, that is radiation. So there are basic some few principles of radiations are like uh, radiations are basically if any object that has temperature higher than the absolute zero temperature, that means inside that material, the molecules and atom, they have some like rotational energy and vibrational energy, and because of that it will like emit those energy like it will transfer from higher energy to lower energy, like that, right? There is some energy exchange will happen into the system if you increase the temperature, right? Because of that, every kind of material that has temperature higher than the absolute temperature will emit some of the emit this kind of thermal radiation, like emit this energy spectrum as a form of thermal radiation. Okay. So so the basic thing is like every material, uh, if every material temperature T is higher than the absolute zero temperature, absolute zero, then in that case it will emit thermal radiation. The reason behind is that uh, there is like inside there is uh, atomic and molecular level energies which emit as a thermal radiation. So if you increase the temperature, then this radiation, the rate of this emission or the radiation will also increase. The radiation rate also increase. And this radiation is basically emit as a way of electromagnetic as an electromagnetic wave basically. So if you like in the course of electromagnetism, you will have a very good idea about this radiation. Okay, but for right now we'll only study about the thermodynamic property. Okay. So if you want to study in terms of electromagnetic wave, you have to study the electromagnetic theory. Okay. So radiation emits as EM wave. And it's like also it's a volumetric property. So that means it's radiation is volume. So that means if you it's directly related to the volume of the system. If you basically increase the volume of the system, so the radiation rate will also increase. So there is a whole spectrum of radiation, as you all know. There are like if you like radiation is basically emits at different wavelength. Okay, so it's starts from like very small wavelengths, starting from like gamma rays to X-rays. Okay, these are like the radiations that has very low lambda values. So lambda is 10 to the power minus 5, lambda is 10 to the power minus 4. Okay, to all the way to very high wavelength radiations are also there, which is like thermal radiations, which has like length to like up to 10 to the power 0 to 10 to the power 2 to microwaves. Okay, 10 to the power 2 to 10 to the power. So these have lambda very high. Okay. Now to catch all of this kind of radiation, there are different types of instruments that they are like to catch gamma rays or X-rays from to catch these microwaves. Okay, so different types of instruments are there. Okay. Okay. Now there are some basic definitions also exist. Okay, so that one of the definition is called the spectral energy density. So I just in a short I will try to write a definition. So because these definitions are very important. So like what are the things like which are unit in the definition of that particular quantity. Okay. Like in some case it's like unit volume, in some case it's unit volume or unit time, in some case it's unit surface area, unit time. So you have to remember all of these things. Okay. So first is the spectral energy density. Since it's a density, so that means it's per unit volume. And so U lambda, it's denoted basically. So this notations are also important to remember. So U lambda is basically spectral energy density. So so U lambda. Okay, so basically U lambda G lambda. What is U lambda G lambda? U lambda G lambda is basically energy per unit volume uh, in the wavelength lambda to lambda plus d lambda. So because the energy, as I have discussed, this uh, radiation has a spectrum of different in lengths of length scale, right? So that means U lambda basically denotes the energy density, that means energy per unit volume at a particular wavelength lambda to lambda plus d lambda. Okay. So it has so U lambda definitely it has unit of energy joule to meter cube into meter, right? So U lambda is a joule per meter to the power 4. Okay. 1 meter is coming because of the volume, and other meter is coming because it's per unit lambda, per unit wavelength, right? Second is the total energy. Total energy density. This is denoted by U. So total energy density, as from the name, it's like uh, U is U lambda into d lambda. The lambda, you have to take all the possible values of lambda that is present into the radiation, that is maybe range from 0 to infinite, any kind of value that exists basically. Uh, so this is integration over all possible values. So this, that's why it take from 0 to infinite. And here, since you're integrating the lambda, so one density will cancel. So U has dimension equal to joule per meter cube. Next is the spectral emissive power. Okay. Spectral emissive power. So spectral emissive power is this is basically radiant energy E lambda. Basically, it's written by E lambda. E lambda. So E lambda D lambda is basically radiant energy per unit surface area into per unit time. Okay. So two things are unit here, per surface area and time. Okay. Into the range d lambda. Okay. The range lambda to lambda plus d lambda. This is the definition of spectral emissive power. Okay. So this is also have energy, lambda as energy joule per meter cube into second. Right? Meter cube into per second. What one is emissivity? What is intensity? It is basically E is basically integration of E lambda d lambda over all possible lambda 0 to infinite. Okay, so it's like integration E lambda over all possible lambda. Okay. This is known as emissivity. So these are very useful definitions. Okay. So E is also have dimension, that means one into one then dimension will cancel, so it will become joule per meter square into second. Okay. These are the pretty much all the definitions we need. One definition is still there, that is the spectral absorptivity. Okay. So fifth one is, this is a dimensionless quantity. Okay. Spectral is denoted by A lambda. So what happens, like when any kind of radiation that is uh, 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 incident on a surface of a system, so it's not like that the whole radiation will be absorbed by the system. Okay, so a particular fraction of that incident radiation will be absorbed by that particular surface area of that particular material. Okay, so that fraction is basically denoted by this spectral absorptivity. Okay, so that means it's defined as the fraction of incident. So the fraction of incident energy absorbed by unit surface area, unit surface area per unit time. So per unit surface area and per unit time. Okay. So let's suppose delta Q lambda, that much of energy is incidentally onto a system. Okay. Delta Q lambda, let's suppose it's like the incident energy per unit surface area and per unit time is incident on a particular surface. So in that case, the amount of energy that is absorbed, delta Q A would be A lambda into GQ lambda. Okay. That is absorbed. Okay. Energy absorbed. So that means if a fraction of energy, so if a fraction of incident energy is getting absorbed, so what happens to the rest of the energy? So So from the rest of the energy, some of the energy will be reflected from the system, and some of the energies will be transmitted from the systems. Okay. So to denote that fractions also, there are two other quantities. One is known as R lambda. This is known as the reflectivity, reflectivity, and T lambda. This is the transitivity. Transitivity. So transitivity, and together all of this A lambda. So to all of these are dimensionless quantities. Okay. So these are all dimensionless. Okay, so if you add all of these things, R lambda, A lambda, R lambda, T lambda, this gives you 1. Okay. So all of these are dimensionless. Okay. These are basically fractions. Okay, the fractions like fractions of incident energy that is getting absorbed, a fraction of incident energy that is reflected, and fraction of energy that is got transmitted. Okay. Okay. Okay, so now we'll let me just briefly denote what is the previous theory of exchange. Okay, so previous theory of exchange. So what this theory basically tells is that first is like if any body has temperature is greater than absolute zero temperature, in that case it spontaneously emits radiation. Emit radiation that we already discussed also in our in the beginning of our discussion. Second is if there are two bodies, let's suppose two bodies are there. Let's suppose one is at uh, T1 and one is at T2, and both in an enclosure. Okay, that means it's isolated, okay, from the rest of the universe. In that case, let's suppose these two bodies are thermal equilibrium with each other. Then in that case, their rate of exchanging radiation. So that means some. So let's suppose this T1 body radiates something which is absorbed by this T2 body. Okay. So that means there is some radiation exchanging is happening into the whole system. So this rate of this exchange will depend on to the temperature of the objects. Okay. So in this case, the radiation exchange rate determined by the temperature of the object. So, obviously, this system should be in thermal equilibrium. Otherwise, this is not thermal equilibrium. And what is the definition of thermal equilibrium for the case of radiation? So, a body that has temperature higher than the absolute temperature. For a body like that, in order to achieve thermal equilibrium in terms of radiation, the spontaneous emission and absorption, both the rates should be equal. Okay. So, a body, if it has spontaneous radiation is equal to the absorption, in that case, it basically signifies that it is thermal equilibrium. Basically, these two rates should be equal. Okay. This radiation rate and absorption rate, in order to achieve thermal equilibrium. These are the three definitions. Next, we'll discuss about the black bodies. Okay, so what is a black body? So black body definition is an object that absorbs all of the radiation incident on it. Okay. So that means from its name, it's quite clear. Like that, we know that black, something. If some object has black color, so it will the black body has a like will be absorb most of the radiations. Okay, so for an ideal black body, whatever radiation that is incident onto the surface of that black body, every bit of that radiation will get absorbed. So that means the absorption coefficient, that is basically A lambda. Okay, that we have already this thing A lambda. This A lambda is basically 1 here. Okay. A lambda is 1. So from this relation, you can tell that R lambda and T lambda should be equal to 0. So that means R lambda and T lambda is also 0. So this is a mathematical definition of a black body. So whatever whenever in a problem, whatever type of problem it is, so if it's mentioned that the system is a black body, so that means you only have to take A lambda is equal to 1, the absorption coefficient. The other two fractions basically will be equal to 0. And this is true for all lambda, it's not for a particular lambda, T lambda, it's for all lambda. So that means for all of the possible lambda values for the radiation that is incident onto the black body, all of the lambda radiation will get absorbed. Okay. I mean radiation for all of the lambdas will get absorbed. Okay. So because of that, there is two significant properties of the black bodies there. One is it's an ideal emitter. Okay. So whatever is an ideal which has an ideal absorption property will be also an ideal emitter. Okay. So it is an ideal emitter. So that means for it has the emission power that is that is maximum for any lambda compared with any other kind of material. Okay, is there or any other kind of object. The second property is it's a diffused emitter. So that means it will emit throughout all the directions. So let's say if this is a black body, so when it emits, it's not emits at a particular direction. It will emit throughout all of the directions like this. So it is a diffused emitter. We'll check what is the property, what is the like different kind of thermodynamic quantity for the case of diffusive emitter and for any directed emitter. So how does this Ferri's black body looks like? So it's like it has this kind of a structure. It's a circular kind of a structure, circular cavity, which has a very small hole here, very small hole. And inside this Ferri's black body, the surface of in the insider surface is made of nearly black material. So this is made of nearly black material. Okay, this inside surface, like it has 99% carbon black, 98% platinum black, and all. Uh, and so whatever radiation that emits from this small hole, it will get reflection from here, 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 so like this. So during each of the reflection, it is get most of its energy got absorbed by the system, and by after a certain time, the whole energy is getting absorbed by this black body. Okay, and this kind of black body is known as Ferri's black body. Okay, this is a type of an ideal black body that we have achieved till now. Ferri's black body. Okay. Okay, so next we'll discuss the intensity of radiation. Oh, this is a very important quantity. What is the intensity? Okay. First, we'll discuss about the directed radiation. So, directed radiation means what? Let me first show you intensity of radiation. So, let's suppose there is a point is there which is basically radiating at a particular direction. Let's suppose this is the direction. It is radiating, and uh, so what is the intensity of this radiation? Okay. So that intensity also depends upon the radial distance from this particular source point. Okay. So let's suppose you want to calculate a particular radial distance r. So what you have to do first, you have to, since we are considering this, it's radiating in a homogeneous way. So what you can do, because of that spherical symmetry, you can draw a circle, whichever radius r. Since we are trying to calculate the radiation at a particular distance r. So let's suppose so at a distance r. So this, let's suppose circle has a distance radius r. Now from here, so the total power that is or from this source point, what is the total energy that is basically coming on to that particular point r, and which is making a particular what is this called solid angle d omega, that given by delta, let's call it as delta w. So delta w is basically E lambda. E lambda we know is the spectral energy, that is per unit time per unit surface area. So total, in order to calculate the total energy, you have to multiply with dt and d omega and also d lambda. Since we know E lambda is the energy between lambda to lambda plus d lambda, so we have to take also consider for all of the wavelengths, you have to multiply with d lambda. Now from here, this is the total energy, okay, that is coming here, like inside this solid angle at a distance r. Now from here, you want to calculate the intensity. So intensity, let's suppose this particular surface area is denoted by ds. So we know that d omega is basically ds by r square. So in that case, the intensity on ds, which is nothing but the energy per unit area per unit time falling on ds. Okay. So that would be, so intensity I lambda d lambda will be equal to d lambda dt d omega by ds. Okay, and g omega we know ds by r square. So if you put it like this, sorry, d omega is ds into r by r square. So if you put it like here, so it will become I lambda d lambda will become e lambda by g lambda. So there is dt is also there. So per unit time is there. So dt. So ds will cancel from here. dt will also cancel. D lambda by r square. And you have to do the integration from 0 to infinite, the whole wavelength range. This gives you the total intensity I. And that means it should be proportional to 1 by r square. Okay. So intensity, that means intensity will be inversely related to 1 r square from a point source. Okay. So yeah. Next is the what is this called? Energy density. Okay, so first you calculate the intensity, next is the energy density. What is the energy density? So uh, in order to calculate the energy density, what is you have to calculate? To basically calculate the amount of radiation that is falling on an unit surface area per second. Okay, so energy density. Okay, so energy density means uh, amount of radiation falling on unit surface area per second. Okay, so um, so in order to calculate this quantity, so what you can do, if let's suppose the radiation has a speed, radiation has speed c. Okay, so that means per unit second it will cover a distance c, right? Per unit second it will cover a distance c. Now so we have to calculate what is the radiation per unit area. So per unit area, so if you consider so this much amount of, let's suppose the radiation that is falling into the surface per unit surface, that is, let's suppose 1 unit surface is there. So that means inside this cylinder of area and at the base as 1 unit, the amount of radiation is there into this particular cylinder will be coming into the unit surface per unit second, right? So we have to calculate the amount of radiation inside the cylinder of length c and surface area of 1 unit. Okay. So so that is nothing but I lambda d lambda, right? Will be equal to c into u lambda d lambda. Okay. So from here you can write I as c into u. So u would be I by c. Okay. This is the expression of the energy density. Okay. And similarly, from this formula you can also calculate the pressure of the radiation. Okay, so pressure of the radiation expression is also same, the density with the density of in a radiation. Okay, so pressure of radiation This all these things are for directional radiation, okay, not for uniform radiation, okay. So, sorry, not that uniform, diffusive radiation, okay. So, the pressure of radiation E is basically also equal to U equal to I by C. These are the formulas. So, radiation energy density is this, and radiation pressure is this, and this is the intensity of the radiation, okay. Next, we will be discussing what is the concept, what is the case for a diffusive radiation. Okay, diffused radiation. So, diffused radiation. So, for the diffused radiation, what you have to consider. So, let's suppose there is a surface that is dA, and onto the surface there is some radiation is coming from every direction. Okay, suppose like this. Now we have to calculate. So it's not like the previous case where there is a the radiation is like emitting from a point source at a particular direction. It's not like this. So instead, here radiation is coming from each of the directions. In that case, what is basically the intensity and other things are uh, yeah. So in order to calculate this thing, what you have to do first, you have to first draw an imaginary surface. Okay. Since it's isotropic, okay, so we can consider a surface. Okay. We can draw an imaginary surface. Okay. Like this. So this imaginary, from this imaginary surface, um, the radiation is basically incidentating onto that our surface of interest, that is given by ds, or it's written at dA, okay, not ds. And let's suppose a small area onto this imaginary surface. Let's take a small element onto this image, the surface onto this imaginary surface is ds, okay, infinitesimal surface. Now, so we have to first calculate what is the surface brightness. Now, instead of intensity, we will consider the surface brightness. Okay, the concept of surface brightness. Okay, so surface brightness. Surface brightness. That is also that means the radiation, the spectral energy per unit area per unit time that is coming from the surface, so K lambda into the range lambda to lambda plus d lambda. Okay. Now, if you calculate what is the expression of this K lambda, so it can be easily calculated. Okay. So if you draw a kind of a solid angle here from the place where basically we are considering the radiation for our calculation right now. So from here, from this, if you consider K lambda as surface brightness, so the radiation that comes through this solid angle and incidentating onto the dA would be K lambda d lambda into d omega, right? And this thing is nothing but the what is the intensity at that particular point, right? I lambda d lambda. Now, And this I lambda d lambda also you can write it as u lambda. I lambda you can write as u lambda. U lambda is I by c, I lambda by c. So I lambda will be u lambda into c. So if you can substitute this thing also here, so in that case it will become u lambda c into d lambda will be a lambda d lambda d lambda. So u lambda d lambda would be k lambda by c d lambda into d omega. Now I have to consider first the whole integration over the whole solid angle. Okay, so this will give you 4 pi. So the integration over the whole solid angle give you 4 pi by c k lambda d lambda. Next you have to do the integration over all the possible values of lambda 0 to infinite. To do that you will get u as, if you do the integration over the whole surface, then it will become total energy density will become 4 pi by c into k. K is the surface brightness of fluid, that is for whole imaginary sphere, for whole sphere. If you consider for hemisphere, the upper part of hemisphere, in that case the formula is 2 pi by c into q for hemisphere. That means this is the expression of basically the energy density for the case of diffusive radiation, diffuse radiation. Now this pressure of the diffuse radiation also you can calculate, okay, by calculating the element of force. Okay, so in this surface area dA, okay, so there is some radiation pressure is there, right? So from this radiation pressure you can calculate the force. The radiation that is coming from its intensity, yeah, from its intensity, you can calculate the force from force that is felt by this particular surface area dA, and from that force, if you divide it by the surface area, this gives you the radiation pressure. Okay, and this radiation pressure is nothing but u by 3. Okay, u is the density by 3. This is the radiation pressure for the case of diffusive radiation. Okay, so for earlier for directed case, it is E is basically equal to I by C or U. In this case, it is U by 3. Okay. Next, we'll discuss a very important law known as the Kirchhoff law. I guess you have already heard about this law in your school times. So let me write it mathematically here. What is the Kirchhoff law is? So the Kirchhoff's law is basically the ratio of spectral emissive power E lambda with the spectral absorption power A lambda. The ratio between E lambda by E lambda for a given lambda, for a given lambda. E lambda by A lambda for a given lambda, it's basically equal to, for all bodies, for a given lambda for all bodies is basically equal to the emissive power of a perfect black body. Okay. Oh, that means E lambda by A lambda is basically given by E lambda by V. That is at a particular lambda is fixed at a particular temperature. So these things should be fixed. Okay. If these two things are fixed, then this is also a constant. Okay. Okay. So this is the definition of Kirchhoff law. Okay. So, what is basically physical significance? Physical significance is this is holds since it holds for every kind of body that exists in our system, in our like universe. So that means if for a body, if you decrease its A lambda, that means the absorption power. So in order to keep this ratio as fixed, the body will also decrease its emissivity power, okay, E lambda. Similarly, if you increase the A lambda, the E lambda will also increase. If you increase the E lambda, the A lambda also of the system of that particular body will also increase. In order to keep the ratio as fixed. Okay. So this is the definition of Kirchhoff's law. Next, we'll discuss what is the like different types of thermodynamic property of radiation. So, so in order to define the thermodynamic relations, thermodynamic properties and relations, what we'll do, we basically consider this radiation, uh, this cavity radiation as an ideal gas. Okay. So why we can consider it as an ideal gas? Because just like the ideal gas, uh, here also the cavity radiation is homogeneous and isotropic, and here also this photon particles. So this radiations are basically made of these photon particles. So, and the photon particles also do not interact with each other. Just like the case for an ideal gas. Okay, so from that analogy, we can consider this cavity radiation as an ideal gas. Okay, so let me write it. So consider cavity radiation identical as ideal gas. So that means we can define a particular pressure, temperature, and volume for this radiation gas unit. For this radiation gas, right? So so first thing that we'll calculate for this radiation gas is the in total energy or the internal energy. Okay. So how to do that? So in order to do that, what we will do, we will first define the energy density. Okay. Since for the case of radiation, you are familiar with not the total internal energy, but the energy density, which is denoted by small u. So small u is basically capital U, total energy divided by the volume. Now, so to get this expression of the small u, we will use the energy equation that you already know. Del u del T is basically T into del P del T at constant T minus P. Now we know that for the case of an diffusive radiation, we know the pressure is basically given by U by G. Okay, pressure is basically U by G. Now, if you use this definition here, and after doing some like integration and algebra, you get the energy density U is simply proportional to T to the power 4, and to take the proportionality constant as A, then it will become U is equal to A into T to the power 4. That means this energy energy density is basically given by related with that fourth order exponent of temperature. Okay. Now from here you can also calculate the total emission energy. Total emission energy would be, you have to just go integration over all possible wavelength. So total emission energy would be from here is given by EA. It is given by sigma into T to the power 4. Okay. Sigma is nothing but AC by 4. C is the speed of the radiation. Okay. And so this particular relation has a name, okay, which is known as the Stephen's law. Okay. Stephen Boltzmann law. So this is known as Stephen Boltzmann law. Now there is this other form of this law is there. So like if let's suppose there are two systems are there. Okay. One is let's suppose at T. One is at let's suppose at T0. Okay. And both the that means these are both of them are let's suppose a black body. So one black body is radiating and one black body is basically absorbing the radiation. So in that case, the total energy that is exchanging during this whole process, that denoted by EA, is basically given by sigma into T to the power 4 minus T0 T to the power 4 EA. Okay. So two system, one is at T, second is at T0, both are black bodies at thermal equilibrium. In that case, the energy that is flowing from one system to another system, let's suppose from T to T0, it's flowing. So that expression is given by sigma into T to the power 4. That means the difference of the fourth order, the temperature difference of it. And it should be thermal equilibrium.
Here, if the energy was flowing from T0 to T, then would this same equation still work?
No, it actually it only flow which from like higher temperature to lower temperature. Okay. So T should be higher
Okay.
than the T0.
Okay.
And this law is for a black body, right? This Stephen Boltzmann law. For any particular any general type of a object, for a general object, this total energy that is emitted, that denoted by QA, that is a total energy emitted would be this xi, sorry, this epsilon into A into sigma into 10 to the power 4. Epsilon is the emissivity. Since for the black body this emissivity is 1, but for a general body this is some fraction values. Okay. So this is epsilon is emissivity. So if you know the temperature and the emissivity of the particular system from for that particular object, you can calculate what is the total energy that has been radiated. Okay. Okay. Now we'll take upon the other thermodynamic quantities. Okay. So first you already discussed the pressure, right? So pressure is so we know U is the energy density is A into T to the power 4. So from here the pressure would be U by 3, right? So U by 3, that means 1 by 3 into A to the power 4. Okay. Now from here, the total energy would be, internal energy would be U into energy density U into the total volume V. That means it would be 1 by 3 AV into T to the power 4. That will be the total internal energy. Okay. Since you got a total internal energy, from here also you can calculate the specific heats also, right? So CV would be del U del T at constant V. That means it would be 4A V into TQ. Now from here also you can also, during this radiation process, what are what are the, let's suppose how much temperature, how much heat has been exchanged, and other things also. If you want to calculate, you can also calculate. So let's suppose you want to calculate during a radiation process what is the value of delta Q, the change in the exchange of heat. So in order to do that, what you have to first consider is the first TDS equation. Okay, so from first TDS equation, what it tells, TDS equal to CV dt plus T into del P del T at constant V dV. Yeah.
Shouldn't the derivative be 4 by 3 AVTQ, like CV value?
Uh, CV, right? Yeah. Yeah,
Yes,
there would be a
yes.
4 by 3. Okay. Hmm. Yeah, there is a 4 by 3. Yes. Hmm. Actually, you can absorb this whole thing into a one constant. Okay. By absorb, you can consider it as B also. Okay. B into TQ. Something
Oh,
like
okay.
that. Anyway, these are some arbitrary constants. Okay, these are specific quantities for specific type of material. The only thing that you need to consider here is the what is the how it is related to temperature. Okay, so total energy is related to T to the power 4. Specific heat is related to T to the power Q. Okay, for a radiation. Okay, for a radiating gas, you can say. Now, for the change in the heat, delta Q, you can calculate from here actually. So, here one thing you can del P del T, you already know. P is basically this. So, from here, del P del T, nothing but 4 by 3 A by TQ, and CV is already know 4A B TQ. So, just by substituting these two quantities here, you can get the TDS is nothing but DQ, right? DQ is basically TDS. So from there you can calculate 4 by 3 ATQ dt plus T by del P del T and V dV. So do the integration. Okay, so integrating this, you will get the delta Q, change in delta Q. So for isothermal process, if delta T is equal to 0, so delta Q will become 4 by 3 to the power 4 into delta V. Thus change in volume of the gas, radiation gas. This is related to the change in heat is basically related to the change in the volume for the case of an isothermal process. Similarly, for an adiabatic process, from the same relation you can calculate. For adiabatic process, let's suppose adiabatic. So adiabatic process, that means delta A is equal to 0. So from the same relation using 1, you can calculate what are the basically equation of that particular radiating gas. You will get, it will be nothing but V T to the power 2 as constant. Okay. From this equation you get V T to the power 2 as constant. Now in this thing, same thing, you can write it as P and V also, using PV equal to KT. you can write as a P b to the power 4 by 3 equal to constant. Okay. Now there are other thermodynamic quantities also there, like one is like the energy functions, as you can see the thermodynamic functions. That is, one is this enthalpy, which is nothing but U plus PV. So U is just energy density U plus V. P we know 1 by 3 A B to the power 4. So U is we know 8 A to the power 4. So this is 4 by, yeah. So this will become A into B into t to the power 4 plus 1 by 3 A B to the power 4. This will become 4 by 3 A B to the power 4. Expression of enthalpy. Similarly, for Helmholtz free energy, that is denoted by F, is U minus Ts. So so you already know. This also you already know. So you put it here, it will give you 1 by 3 A B t to the power 4. Okay. Lastly, Gibbs free energy. So Gibbs free energy also can calculate. So Gibbs free energy would be 0 actually. Calculated H minus Ts, it will give you 0. Okay. Now we'll lastly discuss about the third law of thermodynamics. Okay, so we already know the zeroth law, first law, and second law. So third law. So before discussing the third law, I'm just briefly stating two statements of one is this called learned state theory, and second is the Planck statement. Okay, so the definition of the mathematical definition is important here. So first is the state theory. So what this theory basically tells us that for any isothermal process involving only phases in internal equilibrium, the entropy changes tends to zero as temperature approaches to absolute zero. So for an isothermal process, let's suppose uh, that means if for an isothermal process, if any entropy is changing, so that means there is that's only happens into like for a phase, for a particular phase, right? So let's suppose this change in entropy is denoted by delta S. Now this isothermal process, you are basically doing this isothermal process in the limit T tends to 0. Okay. Sorry, temperature. Delta T tends to 0. In that case, the change in entropy for this isothermal process will be equal to 0. For isothermal process, since T you keep as 0, so that means there is no temperature changes involved here. So that means this process has to be an isothermal process. So for isothermal process, this T tends to 0. This change in the entropy is also equal to 0. Second is the Planck statement. So Planck's statement. So what is this Planck statement is? At T equal to 0, this is known as the standard state. Okay, standard state. the entropy of the state is also equal to 0. So the S should be also equal to 0. If T is equal to 0 at the standard state, the entropy is also equal to 0. This is this is actually useful to do some of the calculation. Let's suppose you want to change the to calculate the change in entropy. Delta, as we know, is delta Q by T, and the temperature is changing from 0 to, let's suppose, T. So that means S by TA minus S by 0 would be equal to dq. So delta Q by T. Okay. Dq is 0 to T. Okay. Yeah. So now this entropy is 0 at 0 temperature is simply equal to 0. So that means this thing is STA. So that you can calculate the entropy at that particular temperature. 0 into TA by del Q by T. And what is the definition of this third law of thermodynamics? So it basically tells us that it is impossible by any procedure, no matter how idealized it is, to reduce any system to absolute zero in a finite numbers of partitions. So that means, what is the third law of thermodynamics states? So third law of thermodynamics. So what it basically states is that it is impossible to reduce any system to absolute zero in a finite number of operations. Now, let's just briefly discuss what is the consequence of this third law of thermodynamics. So, yeah. So we know, first let's see what happened to the heat capacity. So heat capacity, what will happen? So we know delta S is integration Cp dt by T. Okay. Now what happened? So if you make the temperature towards zero, okay. So that means this denominator is also tends to zero, right? Now in that case, the entropy will become infinite. So to prevent that, what will happen? Cp also has to tends to zero. So in order to make this whole quantity as finite, okay. So that means if you plot the heat capacity as a function of temperature, both Cp and Cv, whatever it is, you will see if you decrease the temperature at finite temperature, you know it has this Coulomb-Petit law, T to the power cube law. If you decrease the temperature at T0, it will become almost zero. Okay. Both Cp and Cv. In order to make these things, this ratio as consistent. Okay. Like it is also like experimental, also it is verified. Okay. Second is the expansion coefficients. Okay, so like this expansion coefficient. Let's suppose expansion coefficient. Let's suppose alpha 1 by v del v by del t at constant. Now this thing can write is 1 by v del s by del p minus from Maxwell relation. Now here, if you consider t tends to 0, okay, delta t tends to 0. So in that means delta is also tends to 0. So that means this alpha will also tends to 0. Since here ds is there, so delta s tends to 0. which results to alpha and also tends to 0. So that means the this expansion coefficient also tends to 0 for a particular material if you move it to absolute 0. Okay. Lastly, what happens to the free energies? Okay, like this potentials, thermodynamic potentials. First is the free energy. Free energy, we know free energy F is delta F is basically delta E minus T delta S, which you can write in terms of enthalpy also. Sorry, yeah. So if you make T tends to 0, delta S also will be tends to 0. In that case, delta F would be equal to delta U, right? Change in free energy will be the change in the internal energy. Similarly, if you see the Gibbs free energy, you know delta G is basically delta H minus T delta S. Okay. So if you move T tends to 0, so delta S will also tends to 0, so delta G would be equal to delta H. The change in Gibbs free energy will be equal to change in Helmholtz free energy. These are the pretty much the what like the how the change in the temperature to absolute 0 value will affect the thermal, how it's affecting the different types of thermodynamic properties of a material, okay, of a body, or let me say. Uh, okay, so now we'll do some problems. So the first problem is sunlight falls on the surface of the earth with a power per unit area equal to 1370 watt per meter square. Calculate the radiation pressure. Calculate the radiation pressure in unit of Pascal. Okay, in unit of Pascal. The options are: option A 6.71 into 10 to the power minus 5 Pascal. Option B 4.57 into 10 to the power minus 6. Option C 4.89 into 10 to the power minus 6, and option D 7.89 into 10 to the power minus 4. All are in Pascal. Okay. Now to do it, so it's easy, right? So you know the intensity, you know the radiation basically travels at the speed of light. It's nothing but the photon particle, so it basically travels with the speed of light. So pressure is radiation pressure is given by I by C. So that means I is basically 1370 by 3 into 10 to the power 8. The speed SI is equal to 4.566 into 10 to the power minus 6 Pascal. Next is problem 2. A body which has surface area 5 centimeters square and temperature of 727 degrees centigrade. It radiates 300 joule of energy each minute. What is the emissivity? What is emissivity? Stephen constant is given as sigma is equal to 5.67 into 10 to the power minus 8 over. Watt meter square. The options are option A 0.18, option B 0.34, option C 0.91, option D 0.38. Okay. So emissivity is nothing but energy radiated by that particular body by energy radiated by the black body, right? Black body at that particular same temperature. Okay. So so for the case of a black body, we know uh, the energy density is basically given by density, that is basically U is given by sigma into 10 to the power 4. Now since this is energy per unit area per unit time, so total energy Q would be, we have multiplied it with the area and with the time T, right? Here it is for a minute. Okay, so 60 seconds will be there. Now so this would be for the black body, the total energy. Now the energy radiating from this particular system is 300 joule. Okay, so for this system QE is 300 joule. Okay, so QE is 300 joule, QE is this. Now I have to take a ratio of these two. So 300 divided by A is the total area. So total area is what? 5 centimeter. You have to convert it in meters. So it will then become 5 into 10 to the power minus 4. Time you have to convert it into seconds, 60 seconds, 1 minute it's mentioned. So 60 seconds into Stephen constant is 5.67 into 10 to the power minus 8 into temperature is 7 to 7 degrees centigrade. So it have to convert it into Kelvin. So it will become 1000 Kelvin. 1000 Kelvin. So if you calculate this thing, you will get Z equal to epsilon equal to 0.176. Okay, so that would like almost equal to 1/8. Okay, 0.18. So the option A is the correct answer. So first like so in order to like in the case of black body, we know the whatever energy it will it will emit the maximum energy, right, in the case of black body. So so in order to calculate the emissivity, you have to compare the emitted energy for that particular body with respect to black body, right? And their ratio basically gives us the emissivity ratio. So so by using this formula, you can calculate the emissivity. Next is the question 4. an iron ball surface area of 1000 centimeters square and temperature equal to 527 degrees centigrade is placed in an enclosure is placed in an enclosure at 27 degrees centigrade. If the surface emissivity of iron beam, so if the surface emissivity is of iron beam is 0.3, what is the rate at which heat is being lost by radiation? What rate heat lost by radiation? The option is 86.8 joule per second. Option B is 68.3 joule per second. Option C is 196.6 joule per second. Option D is 145.7 joule per second. So now from here so rate at which the heat will be lost, so that would be the rate of heat loss would be for a particular temperature the energy loss per unit area per unit time that is given by Stephen Boltzmann law, C.2 to the power 4. Here it is, there are two temperatures, right? So temperature will be going from this high temperature 5 to 7 degrees centigrade to 27 degrees centigrade. So and the rate of heat loss, so the total surface area is given, so we have to multiply the Stephen Boltzmann law with the area, right? A and emissivity also, since it's not a black body, so A into epsilon into sigma. From higher temperature to lower temperature it will be radiating, so T would be 527 degrees centigrade, so it will be 800 Kelvin, and T0 would be 27 degrees centigrade with 300 Kelvin. So rate of heat loss would be A into 0.3 into sigma is the same here, okay. The Stephen Boltzmann constant, just the value we have used in the previous problem, 5.67 radical minus 8, 800 to the power 4 minus 300 to the power 4. If you calculate this, it will give you the rate of heat loss as 60.29 joule per second. Question 4. Body of mass 10 gram is at 127 degrees centigrade and is enclosed in surrounding at temperature T equal to 27 degrees centigrade. Okay. Specific heat of the material, specific heat is of the body is equal to 420 joule per kg. Okay. Now per Kelvin, kg Kelvin, per kg per Kelvin, and its surface area is 10 centimeters square. Calculate the rate of cooling. Calculate the rate of cooling. Since the heat is radiating from the system, so it basically cool. So it's kind of a way the heat is getting rid of from the system. So that means the system is trying to cool out. Okay. So the options are, option is 0.29. So the rate of cooling is given by Kelvin per second. So the way like the rate where how the temperature is changing, that you have to calculate. That's basically here used as a measurement of rate of cooling. 0.29, 0.45 Kelvin per second. Option C is 0.95 Kelvin per second. Option D is 0.24 Kelvin per second. Now to get the answer, so first what you have to calculate is what is the heat that is radiating. Okay. Heat that is radiating per unit time. Okay. So it's a, since sigma is so no emissivity is mentioned into the problem, so that means we can consider it as a black body. Okay. So for a black body, the heat that is emitting from like the rate that means per unit time, that would be Q equal to A, the surface area, into Stephen Boltzmann law is equal to T to the power 4 minus T0 to the power 4. Now here the body's temperature is 127, right? So that means 400 to the power 4 minus the surroundings is 27. So that means 300 to the power 4. Okay. Now sigma is the same value here. Sigma is the like the previous one, 5.67 into 10 to the power minus 8. A is the area, that is 10 to the power centimeter square, 10 centimeters square. That means 10 to the power minus 4, 10 into 10 to the power minus 4 meter square. So if you substitute all these things here, you will get Q as 0.9925 joule per second. Okay. So, so this it. So we know uh, for a system how the heat is changing, how the change in heat, that is delta Q at particular temperature dt, is related with mc dt by T. Okay. That we know, right? dq is equal to mc dt, right? So from here we know a dq dt would be mc dt by T. Here T is the temperature and this small t is the time. So dq dt is nothing but the rate how that the heat is changing. That is nothing but the Q. So that means Q is basically mc dt by T. So this dt by T thing have to calculate the rate of change of the temperature. Okay, so dt by T is basically Q by mc. Q is this, mc we know mass is given and the specific is also given. So this would be 0.999925 by m is mass is 10 grams. So yeah, so 10 into 10 to the power minus 3, because we have to convert it into kg. So 10 to the power minus 3 into 420 joule, unit is the fine here. That would be dt by T. So dt by T would be, if you calculate this, it will give you 0.236 Kelvin per second. This would be dt by T. The rate how the temperature is changing. Okay. problem. Close to absolute zero. Temperature, absolute zero temperature. Difference between specific heat goes to, the option A is infinite, option B is R, option C is 0, and option D is none of the above. So we'll just have to write the expression of Cp minus Cv. So Cp minus Cv, you know, Cp minus Cv is Tv alpha by kT, right? Alpha square, I guess, alpha square by kT. So you know alpha is already tends to 0 as temperature tends to 0. That we have already discussed in the previous discussions, right? The volume expansion coefficient basically tends to 0 at absolute 0. That means the Cp minus Cv will also tends to 0. That means the correct option to option C. Okay. Next problem is problem 6. Calculate the ratio of specific heat at constant volume and absolute entropy for a cavity at 1000 Kelvin. The options are option A 1, option B 2, option C 3, and option D 4. The answer would be CV. So CV, we know CV expression is 4 by A B T Q, and S, the entropy is 4 by 4A by 3 into B T Q. Okay. So if you take CV by S, it will give you equal to 3. Okay. So correct option will be option C 3. And the last problem is problem 7. A cavity with volume 5 liter is maintained at 4000 Kelvin for the system calculate enthalpy. Okay. So to calculate enthalpy, so option A is 3.24 millijoule, option B is 0.8 millijoule, option C is 1.29 millijoule, and option D is 5.67 millijoule. So to calculate the enthalpy, okay, so enthalpy, so enthalpy expression is, you know, H equal to 4 by 3 A into V into T to the power 4, where A is nothing but this Boltzmann constant, okay. Sorry, not Boltzmann constant, 4 sigma by C. Sigma is the Boltzmann constant, its value we know. C is the speed of the light or speed of the radiation, that is equal to the speed of the light. So that means it would be H equal to 4 by 3, 4 sigma by 3 into V into T to the power 4. Let's now substitute the values. 4 by 3 into 4 by 3 into 5.67 into 10 to the power minus 8 into volume is 5 liter, right? So so to convert it into SI, so liter you have to convert it into CC. So that means it will become 5 liter is 1000 cc, so it will up to 5 into 0.001, okay, into temperature is 4000 to the power 4, and yeah, C is also there. This C, sorry, this is C. So C is 3 into 10 to the power 8. Okay, now if you calculate it, it will give enthalpy equal to 1.29 into 10 to the power minus 3 joule. That means 1.29 millijoules. So this would be the, so this would be the correct answer. Okay. So this is the last problem for today's class. So if you have any question, you can ask.
Yes, in question number 6, CV should be 4 by 3 AVTU, TQ, right? Because here the constant matters, I think.
CV uh, question number 3, 4 by 3.
Yes, we derived it, right? Du by dt we did.
Yeah, 4
So
by
4 by
3.
3.
CV, there is 4 by 3 is there or just 4? 4a into V into T to the power cube. 4 by 3 was there, right? I forgot.
Yes, yes,
Yes, 4 by 3
yes,
was there. So it would be, that means 1 maybe. Yeah, it would be 1.
yes.
Yeah, that would be okay. So if you have any other question, you can ask. So otherwise, I stop there.
No questions, thank you.
ठीक. Okay, thank you.